So we've looked at the reaction of these metals with oxygen, we've looked at their reaction with cold water, and remember the idea of all these reactions is to try to work out the order of reactivity. Now the one thing about the reaction with cold water is, if you can try and think, it's not that great for actually putting these metals in order because you only actually have information about the top four and how fast they react. For example, you can't really tell aluminium's reactivity apart from zinc's if neither of them react with cold water, so it's not that useful. Our solution to that is our final kind of reaction, just of metals by themselves, which is the reaction with steam. Now steam, just remember, is just hot water. So you're giving the water a wee bit more energy, and that gives these less reactive metals a bit more of a chance to actually carry out a reaction. And remember, if they are carrying out reactions, we've got a better chance of actually working out which ones are very reactive, which ones are not very reactive. So it's the same substance, it's still water, but we're heating it up and we're getting a bit more information about how reactive these elements are. All of them react apart from copper in this case. So if we turn to notes on page 4, we start with our equation. Now this immediately is a little bit confusing at the start. You've got a different equation here than the equation you have for metals with cold water, which should be confusing a wee bit because obviously steam is just water. So you should think it should be the same equation. In this case, we've got metal plus steam going to not metal hydroxide, but metal oxide plus hydrogen. So we're switching the word hydroxide for oxide there. And as you can maybe imagine, that's going to be a point in which you get quite confused in the exam. It'd be a point where people make a lot of mistakes. Now, it's enough for you just to learn that off and take it at sort of face value and just know that when it reacts with steam, it makes a metal oxide rather than hydroxide. You might appreciate knowing where that comes from though. In this reaction, to explain why it's actually different for the same element, it's actually two reactions going on at once here. The first thing that happens when you react a metal with steam is the reaction you kind of expect. It will form a metal hydroxide and hydrogen, which is the same reaction as you have with cold water. The reason it actually goes on to form a different reaction is it's the problem with metal hydroxides. Metal hydroxides aren't that stable at high temperatures, and bearing in mind if we've got steam here we probably are at quite a high temperature. Metal hydroxides will then break down in the second reaction, so this will react further, to form the metal oxide and it'll release a bit more hydrogen. So when you look at those two reactions together, you make metal hydroxide with hydrogen first, then that metal hydroxide decomposes to metal oxide with hydrogen. That gives you this overall reaction here. It's confusing because it's different, even though it's the same substance, just hotter, but you have to remember it is different. So that's the equation, and we'll look at some examples of the simple equations in a second. But let's first of all look at the actual practical method for doing this reaction, because as you can see from the diagram, it's a little bit technical. So obviously this is different in that you have to provide steam to the metal, not just like drop it in some cold water. Producing steam isn't that complicated, but you have to think a wee bit about how you do it practically. This is the setup we use here. So we've got a boiling tube and we've got the metal there we want to react with steam. Our solution for making steam is we put some damp mineral wool at the bottom of the boiling tube. Mineral wool is just cotton wool that's more heat resistant, that's what it means. So when we heat this damp mineral wool, it's going to be a steam, and that steam, the only place it can go is over the metal and potentially react with it. You do still need to heat the metal to get to react, so you notice there's two heating arrows here, and that's an important point if you ever have to draw this diagram. You have to heat it both at the metal and at the mineral wool. You can do that with two Bunsen burners, or you can just move one Bunsen burner back and forward between these two. So when we react this, we're expecting a metal oxide to remain in the tube, but we should expect to make hydrogen as well. So we might want to trap that to prove it actually is hydrogen. So we use the delivery tube at the top of the boiling tube, goes down into this apparatus here, which as far as I know we haven't looked at yet. So we want to trap this technique's called downward displacement of water. Hydrogen is much lighter than water, so if we pass it into the bottom of a tube or vessel that contains water, it's going to bubble to the top and push out any water that's inside it, and it prevents any air getting trapped in there as well, which we don't want. We want pure hydrogen in there. So the setup we have is this. We go into a beehive shelf. Now a beehive shelf is just like a ceramic pot with a hole at the top, and just provides like a wee stand for this jar to go on top. The proper name for this jar on top is called a gas jar, because it's for trapping gases, and it's important that you draw it with water filled up near the top at the start, then it's gradually going to drop as the gas bubbles in. We put this all in a trough of water, just keep it all sealed and stop any air getting in. And it's important that the level of the water level is above the beehive shelf, otherwise it doesn't really work and it'll just escape out the side of the beehive shelf. Again, this is very hard to kind of explain properly when you're just looking at a drawn diagram. I promise we'll go over this when we get back into school. But for now, that's a diagram to react the metal with steam and trap the gas you have produced. There's a little technical point here, it's not too important, but there's a risk of suckback when the heating stops. So if you aren't very careful, if you just heat it, reacts, and you just take the heat away, as this part of the apparatus cools down, it actually can contract and suck water through the delivery tube back into this boiling tube, which isn't great because you've got cold liquid going onto a hot boiling tube. It can cause it to shatter. So you just have to try and pull the delivery tube out at the end of the experiment. Not a very important point. So that's the experimental point. So these are the observations and equations we're meant to know. You might be thinking, first of all, magnesium, aluminium, zinc, iron. There's a few missing here. Correct. Potassium, sodium, calcium, again, are a little bit too reactive to safely do this experiment with in the school lab. And copper's missing because it doesn't actually react at all. It's too unreactive. So we've only got 4 to worry about here. Look at the equations first. So again, it's always worth bearing in mind, you have to be really clear in those general equations. So a metal plus steam, it goes to a metal oxide plus hydrogen. So in this case, what we've got is magnesium. Now steam is still H2O. If we wanted to be really clear about the fact it's steam and not water, we might give the wee state symbol, the gas. It's going to make the metal oxide, so Mg2 plus O2 minus is going to swap and drop to MgO plus H2. In this case, it's actually balanced already. So you can have a go at the next two if you want. Again, just be careful about the iron one, but I'll go through them now. Aluminium reacts with steam to make aluminium oxide, Al2O3 plus H2. To balance that, we're going to need the O's balanced. We need 3 oxygens, so 3 H2O, 3 H2 to get the hydrogens balanced, and 2 aluminiums to get the aluminiums balanced. Zinc, Zn plus H2O goes to ZnO because it's zinc 2 plus H2, that's balanced already. Then the iron one, iron's always tricky, but again, it very rarely comes up in the exam, but they could bring it up this year. Fe plus steam, we'll assume it's going to the mixed iron oxide, so Fe3O4 plus hydrogen. So to balance that out, we need a 4 to balance out the oxygens, a 4 here to balance out the hydrogens, and a 3 here to balance out the irons. So that's the equations done. The only thing left to do is look at the observations. Now at this point you might be feeling a wee bit fatigued by all the observations we've looked at. We've got observations for metals with oxygen, metals with cold water, and also now metals with steam. One wee thing about these observations is there's a little trick for learning them. If you think about it, in these equations you're always forming metal oxides and then bubbles of hydrogen gas. We've already looked at the observations for forming metal oxides. It's the reaction of a metal with oxygen. So if you actually scan down these observations here, they're actually pretty much identical to the observations you have on the first page of your notes where you're making metal oxides. The only difference would be, and maybe I would add it in these notes, is for all of them you're actually going to get bubbles of gas because you're making hydrogen. But apart from that, it's identical to the reactions to make metal oxides, in other words, metal plus oxygen. And you do see the same kind of trend in reactivity. Magnesium is quite vigorous in how it reacts, quite reactive, going down to iron, which doesn't react that quickly at all. So putting this all together, go back in the summary here. We've now got plenty of information to try and work out an order of reactivity. We've got information from reactions with oxygen, cold water and steam. And the kind of consistent thing we see is with potassium, sodium tend to be very reactive, with potassium being most reactive, all the way down to copper being by far the least reactive metal of the set. So the little point we go to here, the little kind of sort of tangent we go off here in the booklet, is a little section about explaining that reactivity. Not in a tremendous amount of detail, but just a little indication of a comparison between the really reactive metals and the really non-reactive metals. It says, recall from year 11, when metals react, they lose electrons to become positive ions. So you take any metal, it's going into a compound and an ionic compound, meaning it's forming an ion. Make that a bit clearer. One really simple example from the first page. Magnesium reacts with oxygen to make magnesium oxide. Balancing that out. If you think about it, the change just in magnesium, starting off as Mg, it's going into magnesium oxide. If we were forming magnesium oxide's formula, we do a swap and drop with Mg2+. So clearly there's a change in the metal. It's starting off neutral magnesium, it's ending up as a 2 plus ion. That's what we mean here when we say that when metals react, they lose electrons, become positive ions. That's going to be true of every single reaction in this topic. When you have a metal reacting, it's going to form a positive ion. So that could come up as a question. We've looked at similar ones before. Half equations, you don't have to overthink them. So 2 questions here. We're at half equation for potassium and calcium. For potassium first, plunk down K. So it's starting off as calcium or potassium. We have to draw as the ion, have to pick the correct ion though. Potassium's in group 1, so that's the form of 1 plus ion, nothing other than that. And to balance out the charges, so it's neutral on the left hand side, it's 1 plus on the right hand side. I need a minus charge to make them both the same, so I stick in E minus. Calcium, same idea, but calcium's in group 2, so therefore it's going to form a 2 plus ion. So to balance out the charges now, I need 2 E minuses to get both sides having the same charge. So that's describing what's happening in all those reactions. You're forming positive ions. So now the question is, well, what's the difference between something that's really reactive, like potassium, and something that's really unreactive, like copper, for example? Again, I said we don't need a really detailed explanation. It's kind of just explained down here in these 2 sentences. The reactivity of metals is related to the tendency of a metal to lose electrons and form positive ions. In other words, and this is the key sentence maybe to highlight or write down, more reactive metals have a greater tendency to lose electrons and form positive ions. So for example, potassium, being a very reactive metal, really finds it easy to lose electrons. That makes it very reactive. Copper, however, wants to hold on to its electrons a wee bit more, therefore it's not as reactive. So it's all to do with just how easily you'll form those ions, how easily you'll lose those electrons from the metal. A more sort of diagram-based form top of page 6. Here's your reactivity series you've got, potassium down to copper. As we're going down, we're gradually becoming less reactive, and that's because we're becoming less likely to lose electrons and form positive ions. So if you're able to remember that kind of key sentence about how these metals lose electrons, form positive ions, you've got everything you need to know there. That just sort of rounds off the kind of reactivity series. Little point here, just think about revision. Technically speaking, you are meant to know the order of reactivity. It's not the most common question. Most of the questions are just about the reactions of the metals. But they could, if they want to be nasty, ask you to fill in a missing metal or fill in missing 3 metals. So you might want to think of a wee mnemonic to try and remember what the order is on top to bottom. The suggested one is please send Charlie's monkey and zebra in cages. So like potassium, sodium, calcium, magnesium, aluminium, zinc, iron, copper. I'm sure you could come up with an even better one than that.